Welcome back to this lecture on microcontroller and its application. In today's lecture, we will be seeing at logic and control and compare instructions which are part of 805 on microcontroller. So let's see what are the logic and compare instructions. So if you see on your screen, you will find all the logic and compare instructions like AND, OR, EXOR, complement, compare instructions. Also we'll be studying about and rotate instructions and swap plus an instruction and some single bit instructions. So all these things form the logic and compare instructions in 805 on microcontroller. So let's see them one by one. So AND instruction. So what is an AND instruction? All of you are well aware about the AND logic. You have studied in digital electronics. You can AND 2 bits. Okay, for example, the AND operation of 1 and 0 will be 0. So AND operation is actually like a multiplying of 2 bits. And if one of them is 0, your answer is 0. Only answer for 1 is when both the numbers are 1. Okay, so this is basically an AND operation. So for AND operation, you have an AND logic in a denomination called ANL. So ANL says AND logic, destination and source bit, destination and source registers. So destination register and source register, okay, these can be destination register is normally an accumulator. The source register can be an immediate data, can be a memory, or can be a register content also. So you can AND maybe ANL accumulator, comma, maybe you can say a register, it is ANDing with, okay, or you can say AND accumulator, comma, hash 40, maybe an immediate data, or maybe even a memory content, that is, maybe it can be a direct address location, maybe 40H, which is a direct address location. So AND logic is possible. In the similar way, OR logic, you know what is an OR logic? And OR two register contents can be ORed in a similar fashion. It can be either accumulator, your destination register can be accumulator, or and your source register can be one of the registers in the register bank, or it can be a direct address location, or it can be even an immediate address location. And the same funda actually follows for EXOR and complement also. EXOR for EXOR operation also. In EXOR operation, you have XRL as the EXOR logic operand, and you have destination and source registers. Destination register is normally the accumulator, and the source register is again one of the registers in the register bank, or it can be one of the memory locations, or it can be even an immediate data. So complement is another operation which also can be included in under logic operation as it is in some textbooks. So in complement operation, you can see complement is done only with respect to accumulator. Okay, you cannot complement the content of any other register. So if you say complement accumulator, if suppose the accumulator content was initially all ones, 0, 0, 0, 0, then accumulator content after complement accumulator will be equal to 0, 0, 0, 0, 1, 1, 1, 1. So all the zeros will get complemented to 1, and 1 will get complemented to 0. So that is what a complement instruction does. Okay, so you have the other for compare instructions, you have one instruction called compare jump not equal. So CJNE is nothing but compare jump not equal. So which compares the content of the destination along with the source, and if the destination and source content are not equal, then it will jump to a relative address. Now this is a statement, compare jump not equal. So compare the contents of two registers, compare the content of two memory locations maybe, and jump to a relative address if they are not equal. So what all ways can this instruction be written? As you can see, it can compare two operands. One of the operand can be an accumulator, that is destination, and the source can be one of the registers in the register bank, or it can be an immediate data, or it can be even a direct address location. The destination over here can also be a register in the register bank. So this is the feasibility of using this instruction. And one more thing to note is whenever the destination is greater than source, carry flag is reset, and whenever the destination is smaller than source, carry flag is set. So based upon these outputs also we can actually invoke a specific operation. That is what is compare jump not equal instruction. So apart from uh, compare jump not equal, you have rotate instructions. You have rotate instructions such as rotate right accumulator. Rotate right accumulator, as you can see in rotate right accumulator, each bit is moved one bit to the right. For every rotate right accumulator, each bit, for example, accumulator if it possessed a bit 1 0 1 1 1 0 1 0, so after rotate right instruction, what happens is each bit will be moved one bit to the right. So each bit will move one bit to the right. So after this operation, the least significant bit will become the most significant bit, and the most significant bit will be moving one step to the right. So this is what happens in rotate right instruction. So your answer will be 0, that is least significant becomes most significant bit, and 1 0 1 and 1 1 0 1. Okay, so after rotate right accumulator instruction, this will be your output. So that is what happens in rotate right accumulator. Now the other instruction is rotate left accumulator, which is straight opposite of rotate right accumulator, in which the most significant bit becomes the least significant bit. In that, the most significant least significant bit moves one bit to the left. Similarly, all the bits in an accumulator will move one bit to the left. This is how this instruction works. Okay, so you have rotate left, then you have rotate right along with carry. This instruction works almost the same way as rotate right. The only exception is the least significant bit becomes the carry bit, and the carry bit becomes the most significant bit. That is one difference over here. So remember, before using this instruction, make sure always your carry flag is reset so that you will not have any bugs. Okay. Similarly, you have rotate left along with carry, in which this is the state opposite of RRC, that is rotate right along with carry. So most significant bit over here is moved to a carry bit, and carry bit is moved to the least significant bit. So you have RLC instruction also. So what is the use of such a instruction like rotate right and rotate carry and all? One of the uses, it can count the number of ones or number of zeros in a particular register. Okay, fine. So that is what is rotate instructions. Apart from rotate instruction, the other instruction you can see as on the screen is swap instruction. So what is a swap instruction? The swap instruction is not like the other swap instructions you have seen. The swap instruction in 8051 swaps the content of two nibbles in an accumulator, and remember, this can be used only with accumulator. So it swaps the content of higher nibble with lower nibble. As you can see, your lower nibble becomes higher nibble, and higher nibble becomes lower nibble immediately after the execution of swap instruction. So that is how the swap operation works. Some of these other single bit operations which we can see on the screen is like set C, set BC, which sets the carry bit, or clear C, which clears the carry bit. Complement is another instruction which is single bit as a single bit instruction we can use to set or reset the carry bit. Now we can use even move instruction to move the content of the carry to a particular bit location, a bit addressable memory location, or we can move one of the bits in the bit addressable memory location to a carry bit. So all these instructions like jump no carry, jump carry, and logic and OR logic can all be used for bitwise operation also. So these are some of the logical operations that we have seen in today's class. So in the next lecture we will see about jump loop and call instruction.